Yeah, I think they'll help your students. Uh-huh. Hey, listen, I gotta go. I'll call you later, okay? Bye, Frank.
Oh, Frank's the reason I'm here. He said he'd leave some papers for me.
Yeah, he did leave them here.
Hey.
I don't know where they are, though. Darn.
I thought you knew all about numbers. Why is this chart out?
Oh, that's for Frank. He may use it in his class.
You and Frank really get into numbers, don't you?
Sure.
I thought you said the number system was simple. Looks pretty complicated on here.
It's not that complicated. Basically, we just have a line with sections sectioned off for whole numbers, and this part of the line starts at 0 and goes on forever in that direction. Great scheme, huh?
You really love this stuff, don't you?
I guess I do. It's really amazing, though. These numbers that are in the whole number spaces, there's just as many of those, say, in between 0 and 1 as there are possible along this whole line, clear to infinity both ways.
Ideas like that are the kind that I understand, but I don't really understand, you know?
Try this. How many whole numbers do you know?
Oh.
Like 2, 12, 200?
Never really thought about it.
How many fractions can you think of?
Who knows? Probably a lot if I tried.
That's it. Nobody knows. Whole numbers are fractions. You can have as many as you can name, forever and ever.
But nobody's ever named them all.
No, they haven't. But each point on this line has a specific name. Yet that same point can have an indefinite number of other names.
Well, that's not so strange. Most people have several names. Well, like sometimes I'm called Todd, or my kids call me Dad, or my dad calls me Son.
Exactly. My wife calls me Dear, or some people call me a number doctor. Probably other people have names for me I just as soon not know about.
Yeah, me too.
And numbers are the same way. Take this one, for example. It could be 1, it could be 1 over 1, 2 over 2, 3 over 3, and so on. It can have a lot of different names.
And the same is true for 2 or 3 or any number.
Right. Except that sometimes people get into trouble when they call something by a name it isn't. For instance, if I call you Bill, you wouldn't answer, would you?
I don't get it.
Do you know what a Bactrian is?
No.
It's a 2-hump camel.
Oh, well, I know what a 2-hump camel is.
Okay. Say we called the humps legs. How many legs would a Bactrian have?
Are the legs still called legs?
Hey, no more help. What's the answer?
Well, there could be 2, or there could be 6.
That's a mistake most people make. No matter what you call them, humps are humps, legs are legs. No matter what you call the humps, the Bactrian still has 4 legs.
That's pretty sneaky, David.
That's it. Hey, arithmetic, algebra, any math I know, it's always the same. As long as you call a quantity by what it is, you're okay. But as soon as you try to call it by some other name, you're in trouble.
That's why you can't add apples and oranges.
Right. Let's see how we would add fractions with different names. For instance, 1/2 and 7/8. We have to change the name of 1/2. We'll change the name, but not the quantity.
Right. We don't want to mix the legs with the humps.
Right. Now, 1/2 is the same as 4/8. So, 4/8 plus 7/8 equals 11/8. Do you see 11/8 on this line anywhere?
Well, it's more than 1, and it's less than 2.
Right.
Is that it?
Right. You notice that that's the same point on the line that 1 and 3/8 is.
Oh. So 11/8 can be called 1 3/8, and it's all the same.
You got it.
That's a pretty slow way to get an answer, though.
That's right, but this is just for demonstration. Okay, but one thing you have to remember. You have to change the name, because we cannot have an improper fraction for the final answer. Now, you know what I mean when I say improper fraction?
Well, they're expressed improperly, not in their lowest terms or simplest form.
Right. Let me show you on the board. So we have our 11/8. This line means to divide. So 8 into 11 will go 1 time with a remainder of 3. We would express it 1 3/8.
But why the 3 over 8?
It's that line again. 3 over 8 with a line means divided by.
Oh, I got it.
Let's try something else on you. Now we have 11 things here we call 8s, right?
Right, 11/8.
Okay, now if we put enough of these together to make 1, it's the same as 8/8, right?
with a remainder of 3/8.
Right. So, what we're saying is 11/8 is the same equivalent as 1 and 3/8.
Yeah, that seems like a pretty good way to explain mixed numbers.
Right. A mixed number is a whole number and a fraction.
This stuff's starting to get to me. I'm going to get out of here.
Hey, we never did find those papers that Frank left for you.
Well, that's all right. I'm sure they'll turn up sometime.
Yeah.
So long, David.
Bye, Todd.
Well, let's hope they do. But with their being on David's desk, who knows? Hi, I'm Steve Wise, and it's good to have you back for another adult math program. Here are some things you should remember from the little talk David and Todd just had. Mixed numbers are most often expressed as a whole number and a fraction, as in 4 3/4, or 4 5/8, or any combination of those numbers which fall on the number line somewhere between each whole number. Take a look at this number line. Though it is a little simpler than the one David has, it shows the same thing. For every whole number, 1, 2, 3, 4, there are uncountable mixed numbers located between each whole number. For example, if you look at the space between the whole numbers 1 and 2, you will quickly see that there is a whole world of new mixed numbers that exist in that small space. Also, you can remember that any point on a number line can have several different names. In fact, it can have an unlimited number of names. Let's take the simple number line again, for example. That spot on the number line, which can be called 1 3/8, could also be called 11/8, or it could be called 22/16, and so on. However, 22/16 is not reduced to its simplest or lowest term. 22/16 can be reduced to 11/8, but it is still an improper fraction because the numerator is larger than the denominator. Remember that the line between the numerator and the denominator means to divide. So 11 divided by 8 equals 1 3/8, which again is just another name for the same location on the number line. Well, I hope that's helped to clarify things some. Now let's get back to the Adult Ed Center and see what's going on.
Hey, Davy. How's it going?
Hi, Frank.
Did Todd pick up his envelope?
He was here, but I couldn't find that stuff anywhere. Hey, you want some coffee?
Sure, thanks. Say, are those the slides there you're going to dig out for me?
Yeah, I got them all ready. Thought we might take a look at them and you can pick out what you like.
Good. Here, I'll hit the lights.
I'll take care of the projector here. Let's see. There we go.
A number line, again.
Here's another version. Okay.
Now, wait, let's look at this one. It wouldn't hurt my class to hear some more about estimating.
Yeah, it's a good idea to remind them. You'll probably want this one next to see.
Good idea. Yeah, unlike denominators. Just plain unlike denominators don't bother my students much anymore, but this is adding mixed numbers. That's different.
These will make them think about estimating before they work the problem, too.
What's next?
4 1/4 plus 2 3/4. You have to deal with this whole number.
Regrouping, you mean?
This next one should follow logically. Let's see. Yep. What happens when you add and the answer is more than the next whole number?
Yeah, that's good. Another kind of regrouping. Now listen, if I need it, do you have one that deals with subtraction of fractions with unlike denominators?
I should have one here somewhere.
It's probably wherever you hid Todd's envelope.
Hey, not funny, Frank. Well, let's see what we got coming up. Okay, here's subtraction and regrouping.
Make the 4 1/4 into 3 5/4 so you can subtract the 3/4. That's a good one for review.
Well, here's the one you were talking about. See, I told you I had it here somewhere.
Well, these ought to help a lot, Davy.
That's it. You're welcome to any of them you like.
Well, thanks a lot. Hey, here's that envelope I left for Todd.
I knew it was here somewhere.
Mm-hmm. And this is that poster you were telling me about?
Yep. Pretty impressive, huh?
Yeah, that ought to make the room look a whole lot better, even if nobody ever understands it.
Hey, they're going to understand it, Frank.
You think so, huh?
Sure, with a little bit of explaining.
Yeah? Okay, here goes. This poster demonstrates what we call a number line. Now, this line doesn't really exist anywhere. It's just a way of explaining how our number system works.
Perfect so far.
Now, one very important thing about this line is that it shows that numbers go on forever in both directions, clear to infinity.
Now, you might want to explain a little bit more about that, them going in both directions.
Okay. This -1 shows that negative numbers, numbers that are less than 0, are also on this number line. Negative numbers are part of our number system, and they also go on forever.
As many negative numbers as we can name.
At regular intervals, on and on forever. Right. And the same thing is true for the positive numbers, the numbers that we usually talk about, 1, 2, 3, and so on until we can't even think of any names for them anymore.
Good. I don't think they'll have any trouble understanding that.
Good. Now for the fractions. Now, between every whole number on this line, say between 1 and 2 or 4 and 5, are an infinity of fractions.
Good.
Now, once again, we can't write down all of the possible fractions that there are because there simply aren't enough spaces. But these fractions exist in our number system, and if we could name them all, they would extend clear to infinity. So, the number system has endless whole numbers and endless fractions. And the fractions help us to talk about pieces of whole numbers or sharing.
Right again.
We can use this number line to help us when we're working with fractions.
Now, that's important because most of them are going to want to know what difference does all this stuff make.
Yeah, they nearly always want to know that. Well, what I'll tell them is this. Say you're trying to work with 1/4. Well, by looking at this, you can see that 1/4 is the same as, or just a different name for, 2/8 or 3/12 and so forth.
Yeah.
And this means that once again we have all kinds of names for what is really exactly the same spot in our number system.
Well, that sounds fine to me, Frank, except you didn't mention the different names for regular numbers.
Oh, yeah, I suppose I should have done that earlier.
You know, it wouldn't hurt anything, I don't think, if you put it when you were talking about fractions.
You think so?
I think it'd be fine. Oh, let's get this thing down in the classroom and let you give it a try.
Okay. You really think I explained this okay?
Oh, sure. Of course, once you get in the classroom, they'll ask you a bunch of questions you never thought of before. You'll have to scramble around to find the answers, but that always happens.
What you should have gotten from this scene is that regrouping of fractions is sometimes required in adding mixed numbers. In regrouping, you express a new whole number in fraction. For example, 4 1/4 plus 1 3/4 equals 5 4/4. 4/4 is the same as 1. Therefore, 5 4/4 would be equal to 6, the new whole number. Another example would be 6 3/8 plus 5 5/8 equals 11 8/8. 8/8 is equal to 1. Therefore, 11 8/8 is equal to 12, the new whole number. Now, subtraction, the inverse or backwards of addition, sometimes requires you to do the opposite. Let's take 6 minus 1 3/4, for example. Since you cannot subtract a mixed number from a whole number, you must change the whole number to a mixed number. Now, since we are dealing in fourths, 1 would be equal to 4/4. You subtract 1 from the whole number 6, and you are left with 5 4/4. Now we have two mixed numbers, 5 4/4 and 1 3/4. They can now be subtracted to get the answer of 4 1/4. Another example of this would be 5 minus 3 2/5. We can call 5 4 5/5 and then subtract. 4 5/5 minus 3 2/5 is equal to 1 3/5. When we change the whole number to a mixed number, we aren't changing the value, just the name of that number. I must caution you, though, when dealing with mixed numbers, you can get different expressions for the same numbers, but be sure when you say one expression equals another that it really does. Remember, no apples and oranges, or humps and legs. Now let's look in on Frank's class and see what's going on.
Okay, let's work through this together, and if you have the slightest question, you stop me, okay? This tells us that we are to add 4 3/4 plus 2 7/8. But we don't have the same denominator, so we must find a common one. Now, in this case, it's 8s. This says that 4 3/4 equals 4 6/8. Now, Bill, how do we find that common denominator?
You can multiply both terms of the fraction by the same number. In this case, multiply both 3 and 4 by 2.
Right, then everything comes out even. Okay, 4 6/8 plus 2 7/8 is 6 13/8. Everyone agree?
Right.
Sure.
All right, now notice this is another one that asks us to estimate the answer. Do you all believe that 6 13/8 is somewhere between 6 and 8?
Well, yes, it is, but I just don't see how you knew that it was going to be between 6 and 8.
Well, Martha, the only way it could be more than 8 is if 4 6/8 were as big as 5 and 2 7/8 were as big as 3, which
Wait
they
a
aren't.
second. Slow down, Todd.
Both numbers are smaller than what they would need to be to make 8.
Oh, okay.
That's
So
right.
that couldn't be 8. And one number's larger than 4 and the other's larger than 2, so it couldn't be less than 6.
That's right, Todd, and that's excellent. I couldn't have explained it any better myself.
Thank you.
You got it, Martha?
For the moment, anyway.
Well, let's go on. If we need to come back, we can, okay? Bill, what's the next step?
Well, that says that 6 13/8 is the same as 6 plus 1 5/8.
Everybody believe that?
And it shows how they got the 1 5/8. 13/8 means 13 divided by 8. Well, that would be 1 with a remainder of 5, which is 1 5/8.
And you combine the whole numbers and it gives you 7 5/8.
There's another way.
What is it, Sue?
Well, in 13/8, just subtract 8 from 13 gives you 5, and call it 5/8.
That's right. All we're doing is subtracting 8 eighths, right? 13 eighths is 5 eighths more than 1. Everybody see that? So our answer is 7 5/8. Okay. Subtraction. Now, we haven't talked very much about subtraction. You all know that subtraction is the backward or the inverse relationship to addition, right? All right. Now, this slide shows us the inverse relationship to the example that we just had. Now, remember, if you get somewhere by addition, you can get back to where you were by using subtraction, right? All right. So, 7 5/8. Well, who would like to show us each step?
Well, I can do it, I think.
All right, Martha, tell us.
4 3/4 can be called 4 6/8, which is what they've done here. Now, 6/8 is larger than 5/8. So what you have to do is regroup the 7 5/8. Now, I can take 1 from 7 and call it 8/8, and then I add that to the 5/8, which gives me 13/8, or rather 6 13/8.
That's right.
Now, 4 6/8 subtracted from 6 13/8 gives me 2 7/8. Is that it?
That is definitely it. That is super. And all the rest of these examples are just different expressions of the same thing. Now, who can give us an example where we can use this kind of computation?
Well, I think I can. Down at the paint store where I work, we sell paint in gallons and quarts and pints. And they'll buy buy some paint and won't use all the pints, and then they'll bring it back to the store to exchange it.
I guess we're lucky that a pint is 1/8 of a gallon, huh?
Right. Well, take this problem, for example. Say on Monday some guy brings in 4 gallons and 6 pints of paint to exchange. Tuesday's my day off, and he brings in more while I'm gone. When I come back on Wednesday, there are 6 gallons and 13 pints. By subtracting, I can find out how many he brought in while I was gone.
Excellent. Good example. Have you got any more to cover the rest of these?
Well, sure. Say somebody pays for 6 gallons and 13 pints, but we only have 4 gallons and 6 pints in stock. Well, I need to subtract to find out how many we still owe him.
Now, knowing we need to subtract is the hard part in real life, isn't it?
Right, there aren't any plus or minus signs.
Well, then how do you figure out what operation to use?
I sort of go by words. If it's how much is left, or how much more, or what's the difference, then I know I need to subtract.
But in a situation like Todd's, there aren't any words like that.
Well, it just takes experience then.
I had something like that come up the other day. I bought a piece of copper tubing, 6 feet long, and I used 2.5 feet of it in the garage and 2 3/4 feet to fix a kitchen sink. Then I needed some of it for the furnace, and I had to figure out if there was enough of it left for that. Can anybody guess how much of it was left?
Sure, it's 6 minus 2 3/4 minus 2 1/2.
Hold this a minute, Martha. Hang on just a second. Nancy, hit those lights back there, would you? Sue,
Want to
turn
start?
that projector off and come up here and show us what you're talking about on the board, okay?
Okay.
But, Bill, why couldn't you just measure the tubing to find out how much is left?
Martha, don't you want an example from real life?
Look, I'll pretend we can't measure, Martha. Now look. 6 minus 2 3/4. Now first we'll rename 6 as 5 4/4 minus 2 3/4. That leaves us with 3 1/4. Now take 2 1/2 and we'll rename it 2 2/4, and take 3 1/4 and rename it as 2 5/4. Now that leaves 3/4 of a foot to fix a furnace.
Is that what you had left, Bill?
That's what I got.
You must be right, Sue.
Oh well, what can I say?
Let me remind you all again how important it is to try to estimate an answer before you work a problem. It can save a lot of time. If you can trust an estimate on a test, for instance, you can get the answer more quickly. Okay, that's it for this week. I'll see you all next time.
Oh, wait a minute. I got this great problem that the guy at the store told me the other day. Are you ready for this one now?
Yeah.
Okay.
If a hen and a half can lay an egg and a half in a day and a half, how long would it take 6 chickens to lay a dozen eggs?
Now, wait. Does this mean that one hen can lay 1 egg in 1 day?
Ah, that's too easy.
Well, you all go on and figure it out, all right? I've got to leave.
Well, what does it mean, Todd?
Well, it means just what I said.
Well, tell it again.
If a hen and a half can lay an egg and a half in a day and a half, how long would it take 6 chickens to lay a dozen eggs?
I don't.
Forget it.
If a hen and a half could lay an egg and a half, well, as usual, Todd has the class and me thinking. I have a feeling we'll be hearing from him again on that problem. Okay, let's test your memory on this section of the program. How many key words did you hear that told you what operation in arithmetic you should use? Did you hear more than, less than, how much is left, compared to, greater than? These are all key words or clues that let you know that you should subtract. For example, if I told you there were 6 apples and I took 3 and asked you how many were left, you would have to subtract 3 apples from 6. Did you hear the key words, how much altogether, combined, or total? These are all clues that you should add. Now let's say Bill ran 4 miles yesterday, 3 miles today, and is going to run 3 miles tomorrow. Then I asked you how many miles altogether will Bill have run? Or maybe I would ask you, how many miles combined will Bill have run? Did you catch the key words in the questions that told you to add how many miles Bill had run? What about Sue's shortcut? If the improper fraction is more than 2, what does Sue do? In 13/8, Sue thinks 13 minus 8 equals 5, so 13/8 equals 1 5/8. What would Sue think about the fraction 19/8? Oh, by the way, how many eggs would 3 chickens lay in a day and a half? Think about it. I'm Steve Wise. See you next time on Adult Math.